Hi everyone. Let's say we are given an insulating sphere with a positive charge Q distributed uniformly among that sphere. And the question is, we need to find the electric field inside that sphere, along the surface and outside the sphere. And let's say that the sphere has a radius of capital R. And the radius of the sphere is capital R. So how do I use Gauss's law to find the electric field inside on the surface and outside? So first we take a Gaussian surface inside the sphere, a circular or spherical Gaussian surface that looks like that. So let's make it dotted to say that it's an imaginary surface. That's the spherical Gaussian surface of radius small r. And we apply Gauss's law. So Gauss's law says that the closed integral of the electric field dot dA is the charge enclosed divided by the epsilon zero. By symmetry, this electric field is going to be uniform along the surface of the Gaussian spherical surface. So we can take E outside. The integral of dA, the area of this Gaussian surface, is simply 4 pi small r squared. Now what is Q enclosed? So Q enclosed, I can find the Q enclosed using the formula. Since the charge is distributed uniformly, then Q enclosed is equal to the volume charge density rho multiplied by the volume where the charge is enclosed in. This rho, it's the total charge Q. Let's say the charge distributed is Q. So it's the total charge Q over the total volume of the sphere, which is 4 over 3 pi capital R cubed. The volume enclosed, it's the volume of the Gaussian surface, 4 over 3 pi small r cubed. So Q enclosed becomes capital Q. We know that those terms cancel, 4 over 3 pi, 4 over 3 pi. So we are left with small r cubed over capital R cubed. Now we substitute this result. We substitute that result in Gauss's law. So what will you get then? So Q enclosed is simply capital Q, as we have seen, small r cubed over capital R cubed, epsilon zero. So electric field will be Q. Now R cubed small with R squared, we are left with R. We are left with R. And in the denominator, we have 4 pi R cubed epsilon 0. So that's the equation of the electric field inside the sphere. And obviously the relation between E and R, it's a linear relation. Later we'll plot the graph. Now this is, as we said, the electric field inside. That's inside the sphere. Inside the insulating sphere. What's the electric field outside the insulating sphere? So outside the insulating sphere, so that's the sphere again, which is positively charged, charge distributed uniformly. Now we take a Gaussian surface outside, because we need to find the electric field outside. We take a spherical Gaussian surface outside the insulating sphere. Okay, and we find the electric field. the magnitude of the electric field. And by the way, the direction of this electric field is going to be radially outward. Inside the sphere, this electric field is going to be directed radially outward. So it looks something like that. Okay, that's the electric field inside the sphere. Now outside the sphere, again, this electric field will be directed radially outwards again. Will be directed also radially outwards. That's the electric field. And we use again Gauss's law. So Gauss's law, the closed integral of E dot dA is also the Q enclosed. Now the Q enclosed is simply the total charge Q, because the whole charge is enclosed in the Gaussian surface, over epsilon 0. So E multiplied by 4 pi, again R squared. Now here, this is R. This is a small r. So here, small r, for this example, small r is bigger than the radius of the sphere, while in the previous one, small r is smaller than the radius of the sphere. Okay. Then this is equal to Q enclosed over epsilon 0, or Q over epsilon 0. So E becomes Q over 4 pi epsilon 0 small r squared. That's the electric field outside the sphere. If we want to plot the magnitude of the electric field versus R, so that's the electric field, and this is R, and this is the radius here, let's say 0, and here R. So for R smaller than R, for R smaller than R, the electric field is proportional to the distance. So the relation is linear. Then the graph is going to be simply a straight line for R smaller than R. Exactly at R equal R, you can take any of those two equations. You are going to get the value of this electric field, Q over 4 pi epsilon 0 capital R squared. And for R bigger than R, you can see the relation between E and the electric field and the distance, between E and the distance, inversely proportional to square of the distance. So it's going to be a curve, a decaying curve, or a curve like going down. That looks like that. So the maximum value is simply going to be at R equal R. That's the maximum value of the electric field. It's going to be at R equal R. For R smaller than R, it's linear. For R greater than capital R, it is a curve going down.